Good morning, everybody, and welcome back to Next Door NetAdmin. We're back for an actual demonstration this time. It's a wonderful thing. I'm going to continue talking about IPv6, and today specifically, I'm going to talk about SLAAC. No, I don't mean that I'm just a slacker, although that's a wonderful bit of punnery that I deeply enjoy. In this case, SLAAC, spelled SLAAC, is stateless local address auto configuration, or something similar to that. Don't quote me on that. But the most important part of this is the stateless part. If you think about IPv4 in comparison, you know that DHCP is a service that you run so that when network nodes boot up, they can request an address and something will assign an address to them. Okay, that's fine. And yes, you can do DHCP and IPv6 as well. The protocol is there. But IPv6 said, you know what would be cool is if we say that we don't have to have that anymore. How about we make nodes able to determine their own addresses? This is not unlike the APIPA addresses that you can sometimes see in IPv4. They always start with 169.254.x.x. And those are automatic IP addresses, but there's no expectation that a node can actually use these addresses to access the internet or other services. They're just automatic IP addresses that sometimes show up on interfaces when nothing else is received, either via static configuration or via DHCP. So IPv6 said, you know what, it would be great if we had something that nodes can configure themselves without relying on a network service. But then how are they actually going to build a global address so that they can talk to other devices online? SLAAC is how we do this. SLAAC and router advertisements. And I'm going to show you both of them. But let's start with, what does a node know when it boots up and it says, oh, I've got a network card? What does it know? It knows the MAC address, because this is usually something that's burned into the card itself. And if you're not using that, then you've overridden it with something else configured. Okay, fine. But it knows the MAC address. And it knows that a MAC address is 48 bits in size, usually expressed as 6 pairs of hexadecimal digits, so 48 bits. In IPv6, addresses are 128 bits large. But most of the time, you're going to look at 64 bits for the network portion, including subnet, and 64 bits for the host portion. SLAAC only works on /64 subnets. That's an important thing to remember. For all intents and purposes, this is the smallest normal subnet that IPv6 imagines. So that's what it operates on. But you have 48 bits in a MAC address, and you need 64 bits for the host. So it makes sense that you can use the MAC address of the computer to help construct this address. And I'm going to show you a graphic that explains this, and all credit to, if I bring it up here, there we go. All credit to networkacademy.io, from whom I am absolutely borrowing this. But you start with the MAC address, and this is all in hexadecimal, I'm going to point out. So this is not technically 70. This is in hexadecimal. This is not decimal 70. This is 70 in hex. Or 011100000 in binary. Okay. But you start with that. You split the MAC address right in the middle. The OUI, the organizational unique identifier on one side, and then the device ID on the other side. And you slap FFFE right in the middle of it. It's just what you do. Okay. Well, you now have something that is 64 bits in width because you've got 8 pairs of hexadecimal digits rather than 6. And we're done, right? No. You flip the 7th bit of the MAC address. Why do you flip this bit? This is, in some respects, just to make it more unique, I would say. Technically speaking, the 7th bit of the MAC address is the universal or local bit. It indicates whether this is a universal address that is supposed to be unique among all devices that have been created by humans, I guess, or whether this is a locally administered address. That 7th bit, if it is 0, then it is a universal address. And if it is a 1, it is locally administered. It's not going to have the same meaning in SLAAC because this is an IP address for a start, and this is not abiding by the same rules for another. But in most cases, it's going to go from 0 to 1 because most MAC addresses are universally assigned, and therefore the 7th bit will be 0. But it's not always going to end up as a 1. If, for whatever reason, you're using locally administered MAC addresses, and the 7th bit is a 1, then when it flips, it's going to become a 0 in this 64-bit interpretation expansion of the MAC address. But once you've performed that step, you now have a 64-bit identifier for your host. And in this particular graphic, it starts with combining the link local prefix with this 64-bit identifier, the EUI64 identifier. And since the link local prefix in IPv6 is FE80, then you now have an IPv6 link local address for the interface. Cool. Now what? Are we done? We're just getting started. This is the conversion from MAC address to IPv6 EUI64 identifier. Once you have a link local address, you want to make sure that nothing else on the network is using that address. IPv6 has a protocol for this. It's called DAD, Duplicate Address Detection. It's similar in concept. If you think about in IPv4, many DHCP servers will ping the address that they're about to assign just to make sure that nothing's actually using that address before it assigns it to another station. Duplicate address detection is kind of the same thing, except it's done by the host because the hosts can construct their own addresses. So when it has a link local address, okay, it's going to do duplicate address detection to make sure it's not about to collide with another station that's somehow constructed or was manually configured with this address. Why are we bothering with link local addresses at all? Well, that comes to the second portion of this, which is router advertisements. Once you have an IPv6 link local address and you can properly listen to and query traffic on the line, routers that are running IPv6, most of them will send router advertisements. It's just a thing that they do. But a station can also send a router solicitation, which a router will respond to with a router advertisement as well. If a station is feeling particularly impatient. And a router advertisement will include a few things. Number one, it will include the router's address. And it will also, as a part of that, include the subnet that the router is on. So when this router advertisement is received by the station, then it knows what subnet it's on. And it knows where its gateway is because it knows that this came from a router. And you can even hear multiple routers, possibly. And the client can say, oh, there are multiple routers on my subnet. I could use either of them. Cool. Now that it has the subnet, it can take that same EUI64 identifier generated from its MAC address and use the subnet from the router to create what should be a globally accessible IPv6 address. And then it'll perform duplicate address detection again to make sure that nobody's using this new IP address that it just, concocted. But after that, it's off to the races. What's missing from this process that you would typically see in DHCP? The most obvious thing is DNS. How do you do DNS? All we have is a local IP address and a gateway. We don't have any DNS information. IPv6 is meant to function with multicast DNS, where stations can just broadcast their queries to the network, and hopefully they'll be picked up by, a server and processed. But in many cases, that's not something that exists. Apple protocols that are implementing Bonjour will often respond or broadcast their multicast DNS there. But it's not universal, and I haven't seen a lot of that in corporate networks. So SLAAC, the router advertisements, have additional bits that can be toggled to tell the stations if there's other information that they should be listening to. I'm actually going to show this to you in OpenSense because I have an OpenSense box here with some VLANs configured for router advertisements. And I want to draw your attention to these two modes. One is stateless and one is unmanaged. What's the difference here? Well, if we look at the one for my imaging VLAN, which is currently in the unmanaged mode, you can see that there's absolutely nothing listed here for DNS settings. Also, absolutely nothing here for routes. There are no specific routes. This is purely IPv6, and you have to figure out your own DNS settings. You'll get an IPv6 address that you can concoct, but that's about it. And if we look at the help for the mode, this is to say which flags are going to be set. I don't like the way that OpenSense explains these currently because it's not particularly clear what these do, because they're talking about stateless address, auto configuration, and DHCP v6. But auto configuration is not something that's in this drop-down box. Use router only to disable stateless address auto configuration SLAAC and DHCP v6. Use unmanaged to enable SLAAC, managed for stateful DHCP v6, assisted for stateful DHCP and SLAAC, or stateless for stateless DHCP v6 and SLAAC. What is all of this? Let me see if I can break this down for you. SLAAC, stateless address auto configuration, is designed to work on its own. Yes, absolutely. DHCP v6 can run in two different modes, stateful or stateless. In stateful, it works the same way as DHCP v6, or excuse me, the same way as DHCP v4. The server assigns the address, maintains a lease database, and stations are only allowed to use the addresses that they get from the server or whatever they're configured with manually, because the admin's always able to override that. Stateless DHCP v6 is slightly different. It's less about assigning an address and more about providing information. And so when you've got unmanaged, you're going to use SLAAC, and that's it. Managed, you're going to use stateful DHCP v6, and that's it. Assisted, you're going to do both. And I don't know right off the top of my head why you would do both, but I'm sure that there's a reason. I just don't remember what that reason is right now. The interesting for me, really interesting thing for me is this stateless, where you've got stateless DHCP v6 and SLAAC. And the reason I don't like this terminology is because if we take a look at my data VLAN, hey, guess what? This is not information that's being provided through DHCP v6. I'm using this to provide a DNS server address, a corporate DNS server over IPv6, but I'm doing it directly through router advertisements instead. And so with this stateless setting, technically it's the A flag for auto configuration, and it's the O flag for other configuration. That's what the O flag is, other. And the M flag is managed. So you've got three flags here: automatic, auto configuration, managed, and other configuration. If you have a router advertisement with the A flag, then stations know that they are allowed to construct their own addresses. If you have the O flag set, it knows there is other configuration in the router advertisement packet. And in this case, it's a DNS server. Here is a DNS server that you should use. Ta-da! Great. You can do the same thing in Cisco configuration, in iOS XE, because I've done it before. I don't remember the command right off the top of my head, but I know you can do it. And I had to set it because otherwise it doesn't know to include it in the router advertisement packet. Cisco devices will happily send router advertisements all day, and that can be included with the A flag, but it will not send the O flag unless you tell it to do so and give it the value, in this case, DNS server, that you want it to advertise. You know what? Just for fun, give me a second. I'll actually pull up the command because now I want to. Having talked about it, I want to. Okay, I found the relevant configuration file and I've pulled it out. Pardon me for all of the stuff. This was actually from a working corporate environment, so I'm having to blur out a lot of the information. But the most important thing is you can see that we've got an IPv6 address, and then we're telling it to add ND other config flag. ND in this case, I believe, is neighbor discovery. This is actually controlling the router advertisements, or at least it was in this version of Cisco. And keep in mind that commands may change. But then you say, first you say, I want to add the other config flag, and then you say IPv6 neighbor discovery router advertisement DNS server, and then you have the server address. So this is how you can actually set this up so that your stations all configure themselves with their own addresses. You don't have to run DHCP in IPv6. You can if you want, and set your router advertisements to tell them, hey, get it from DHCP. If you have managed, it's got M and O flags, then it knows that it's not supposed to auto-configure itself with SLAAC. It needs to actually do a DHCP process instead. And the station will switch to doing that if it needs to. But you can set this up so that stations can construct their own addresses. They're going to be based on the MAC address of the station, so they're going to be reasonably unique. But then you can still pass other information, such as a domain controller for DNS or other desired DNS addresses as well by adding the other config flag. And that's how I like to run my IPv6 networks. Obviously, there's many different ways of doing it, but that's the way that I like to do because it means I don't have to run a DHCP server and keep track of a lease database. I can let the nodes configure themselves, but I can still point them in the right direction for DNS, which is what I needed to do. It's useful to note that one of the things that you should keep in mind here is if stations are all going to configure their address based on their MAC address, then when they're using their global address, they're also advertising their MAC address to everything else that's out there on the internet. This may not be what you want, because then you can just look at the host portion, the last 64 digits of the address, and say, oh, I saw it come from this subnet, and later I saw it come from this subnet, and later I can. This is a single device, a single MAC address that's moving around from network to network. And you could actually start to build up a profile of the device's location. IPv6 added privacy extensions. A station may have its fixed MAC address and therefore a fixed EUI64 identifier that it can use to construct a default address. But then once it's got router advertisements and it's got link local address and everything else that it needs, it can, and certainly in Windows it's default, it can generate other addresses that it will use temporarily in order to actually communicate with the internet. In Windows 7, at the very least, these addresses were listed as temporary. Possibly it was in Windows 10 as well. They're not explicitly listed as temporary in Windows Server 2022, which is what this particular server is. So I can't show it to you, but a station can and will generate multiple temporary IP addresses in IPv6 so that it can use these and cycle them out and preserve some privacy for the node that is actually using it. So you can use the MAC address to get yourself online, but then in order to preserve the privacy and prevent the device from being tracked across multiple networks, it can generate private addresses that are temporary and keep cycling those out as it goes. So that's something that's pretty cool to keep in mind as well. So hopefully this has been interesting and enlightening for you. If you have questions about how this works or thoughts on other things that you would like to hear me talk about or see me demonstrate, feel free to let me know right down there in the comments section. Otherwise, thank you very much for watching. I am your next door net admin, and we will see you next time.